So now we have this Euler's equation, this one. So I write it again, 1 by 2 dv square plus dp by rho plus g dy equal to 0. So by using this general form of Euler's equation, we can also drive the Bernoulli's equation. Okay. So for driving Bernoulli's equation, now we integrate this Euler's equation. Okay. So I am going to integrate this Euler's equation. So I integrate all these terms in this Euler's equation. Okay. So when I integrate first term, it becomes v square by 2. The second term, it is p by rho. The third term plus gy is equal to constant. So this is the one form of Bernoulli's equation. V square by 2, p by rho plus gy equal to constant. Each term represent energy per unit mass. So that means the first term gives us the kinetic energy per unit mass, that is V square by 2. P by rho is the pressure energy per unit mass. And third is the potential energy per unit mass. So in this equation, each term gives us energy per unit mass. यहाँ दूसरे वे में आप ऐसे भी कह सकते हो. Now see the unit of this term. The unit is meter square second square. Meter per second और square के साथ है, it becomes meter square second square. Multiply this by kg, divide by kg. Now you rearrange the terms. So on top you can write meter into kg into meter per second square divided by kg. ठीक है, kg kg से cancel हो जाएगा, second square meter square. Now this you can also write equal to, now this kg into meter per second square is mass into acceleration. So we can write it as force, that is Newton. Newton meter upon kg. So Newton meter is energy. Okay, energy per unit mass. So that means in this equation, each term represents energy per unit mass. Okay. Now energy per unit mass. Now if I divide in this equation all terms by g. Okay, if in this equation I divide all these terms by g. Now I can write again the Bernoulli's equation as v square divided by 2g p by rho g plus y equal to constant. This way, or you can also write it as v square by 2g plus p by rho g is w, specific weight, plus y equal to constant. Okay, so in these two equations, each term represents energy per unit weight. Okay, so in this equation or in this equation, each term represents energy per unit weight. Now energy per unit weight, this term we also call as head. So that means in this equation, first term represents the kinetic energy per unit weight. That means this is kinetic head. You can also call it as kinetic head. The second term represents the pressure energy per unit weight. This term is pressure energy per unit weight. So we can also call it as pressure head. The another name is static head. Okay, the another name is static head. Similarly, third term is the potential energy per unit weight, and we call it as elevation head. Okay, the another names are, you can note down, the other names are position head. Okay, there is one more name. This is also called potential head. Okay. Now the sum of these three that we call as total head. Okay. This is called as total head. The another name is hydrodynamic head. Okay. So that means V square divided by 2g p by plus p by w plus y is total head or hydrodynamic head. Okay. So this equation is the another form of Bernoulli's equation. Now, if I write this Bernoulli's equation in term of a statement, okay, if I write this equation in term of a statement, then that becomes Bernoulli's theorem. Okay, so you can say the statement of Bernoulli's equation is Bernoulli's theorem. Okay, so now I can write the statement of Bernoulli's theorem. So it can be stated as, or it is stated as the sum of kinetic energy, okay, pressure energy, and potential energy per unit mass of a steady, okay, ideal and irrotational fluid is constant along a streamline or at a point. So this is the statement of Bernoulli's theorem. Okay. So you can also state it in another form. It is stated as the sum of, you can write here kinetic head. Okay. You can write here put pressure head, and you can write here potential head. So फिर per unit mass नहीं आएगा. Head means it is energy per unit weight. So that means it is stated as the sum of kinetic head, pressure head, and potential head of a steady, ideal, and irrotational fluid is constant along a streamline. ठीक है. Along a streamline हमने क्यों कहा? कि ultimately जो fluid element हमने consider किया था, that must lie on some streamline that is similar to a point and lie on a one streamline. Okay, so this is the Bernoulli's theorem and the Bernoulli's equation. Okay, now I start with next topic, that is impulse momentum relation. So this relation is based on momentum principle. This is based on momentum principle. So according to momentum principle, the time rate of change of momentum is proportional to the applied, or you can say impressed force, and takes place in the direction in which force acts. So this is the momentum principle. So if I try to write in form of equation, we can write it as F is equal to d by dt of momentum mv. Okay. Now if I try to open this derivative, I write this equation as m dv by dt plus v dm by dt. Now here this v is velocity, m is the mass. Okay. So m dv by dt plus v dm by dt. Okay. So now I put one assumption over here. Now if say the flow is steady flow. So steady flow, then the mass flow rate is constant. So you can put dm by dt as 0. So for steady flow, we can write the momentum principle that becomes as F equal to m dv by dt, or you can write F into dt is equal to m into dv. Okay, so this equation we call as impulse momentum relation, because F into dt is the impulse and m into dv is the change in momentum. Okay, now impulse means this is the applied force in a unit time.
Short period of time.
Okay, in a short period of time or in a unit time, that we call as impulse. So impulse is equal to the change in momentum. Okay, so this is impulse momentum equation. If I write it in the form of a statement, that becomes impulse momentum theorem. Okay, that becomes impulse momentum theorem. Okay, so I write its statement. The impulse due to force acting on a fluid mass in a small interval of time is equal to change in the momentum of the fluid mass. Okay, so this is impulse momentum theorem. Okay, so the impulse due to force acting on a fluid mass in a small, the force, not impulse, the force acting on a fluid mass in a small interval of time is equal to the change in momentum. Okay, so this is impulse momentum theorem, and this equation is impulse momentum equation. Now I use this equation to find out the force exerted by fluid on any bend. That means, say, if I have a pipe like this is a pipe. Okay, so this is one section, this is another section. ठीक है, some fluid is flowing through this. So say some liquid is flowing entering through this in this side and leaving from this side. ठीक है, when liquid changes its direction in any pipe, so that liquid applies force on this bend, that applies some force on this bend. ठीक है, so if I have to find out that force, so I have to use impulse momentum relation. ठीक है, किस तरह से हम फाइंड आउट कर सकते हैं? Now say we have this pipe now. Now in this pipe, say liquid enters from this side and leaves from this side. Okay, so this section is AB. Okay, and this is CD. Okay, so at the entrance, the velocity, so that is the normal velocity, is V1 makes angle θ1 with the horizontal. Okay, similarly here, the velocity is V2 makes angle θ2 with the horizontal. Okay, now say after time dt, जो सेक्शन ए बी है that moves to, the section AB moves to A dash B dash. Now say that distance is ds1. Similarly, the section CD moves to C dash D dash and the distance is say ds2. ठीक है, जो फ्लूइड सेक्शन ए बी पे था, या लिक्विड जो सेक्शन ए बी पे था, आफ्टर टाइम dt it moves to A dash B dash. So this movement is with respect to velocity v1, and the section CD moves to, ठीक है, section C dash D dash, the distance is ds2. Okay, this is for very small time dt. Now I am writing the mass, fluid mass, which is entering, that is this one. Okay, the fluid mass which is leaving is this one. So mass क्या हो जाएगा अब? Density at the entrance multiplied by volume. ठीक है, so volume of A B B dash A dash. Okay, so I write the mass. ठीक है, ये रीजन आ गया मेरे पास. इस रीजन में कितना मास होगा? So for steady flow through this pipe, you can write ρ1 A1 ds1 is equal to ρ2 A2 ds2. ठीक है, अब मास आपके पास है एंट्रेंस पे, मास आपके पास है लीविंग पे, सो यू कैन आल्सो राइट इट्स मोमेंटम. ठीक है, मास को अगर आप वेलोसिटी से मल्टीप्लाई कर दोगे तो यू कैन राइट द मोमेंटम. ठीक है, सो नाउ आई एम ट्राइंग टू राइट मोमेंटम ऑफ फ्लूइड मास इन रीजन सेम, दैट इज ए बी बी डैश ए डैश. तो ये मास है, तो इसका मोमेंटम हो जाएगा ρ1 A1 ds1 into v1. ठीक है, सिमिलरली मोमेंटम ऑफ फ्लूइड मास in region, the top region, that is C D D dash C dash. So this comes out to be ρ2 A2 ds2 into velocity v2. ठीक है, now I write the change in momentum. The change in momentum is the momentum of leaving mass minus the momentum of entering mass. So I write it as ρ2 A2 ds2 into v2 minus ρ1 A1 ds1 into v1. This is change in momentum. Now, according to impulse momentum equation, the change in momentum is equal to impulse F into dt. Impulse on fluid which is in this area. Impulse on this fluid. ठीक है, अब ये थोड़ा आगे भी चला जाएगा यहां तक. Impulse on this fluid that is within the pipe. So this impulse is equal to ρ2 A2 ds2 into v2 minus ρ1 A1 ds1 into v1. Now what is ds? This is ds2. Now what is ds2? ds2 क्या है या ds1 क्या है? The distance. ds1 is the distance moved by AB with velocity v1 in time dt. ठीक है, in time dt. So distance को आप लिख सकते हो velocity into time. You can write distance as velocity into time. So I write it as rho to A2. This distance is velocity into time into V2 minus rho 1 A1. Again, velocity into time into V1. Okay? Now, if the fluid is incompressible, I put one more assumption here. Fluid is incompressible और ideal भी है fluid तभी आप कह सकते हो क्योंकि हम viscous force consider नहीं कर रहे और incompressible भी अगर आपके पास fluid है तो क्या होगा rho 1
Density
equal
is
to rho 2 equal to rho. ठीक है तो अब इस इक्वेशन को अगर आप दोबारा देखो so your dt term cancels out. F you can write as now density common take it out rho 1 equal to rho 2 that is rho. ठीक है now A1 V1 equal to A2 V2. ठीक है that is discharge. So I write A1 V1 equal to A2 V2 equal to Q. ठीक है so Q I take outside rho Q और ब्रैकेट में आपके पास रह गया अब V2 minus V1. ठीक है ये इक्वेशन रह गया आपके पास. What is the meaning of this force? This is the force acting on this fluid जो ग्रीन कलर से मार्क किया. ठीक है जब किसी बेंड के थ्रू पाइप के थ्रू फ्लो चलेगा so this equation give you the force on fluid. अगर आपने इसे रिवर्स निकालना हो इसका रिएक्शन निकालना हो the force by fluid on the bend on the pipe so I can write it as F equal to negative of this rho Q V1 minus V2. ठीक है this is the force exerted by a fluid on the pipe or bend. ठीक है so now we have this equation. ठीक now further you can see here now for V1 velocity is a vector quantity. Okay we can resolve it along x direction and y direction. X direction component is V1 cos theta 1, y direction component is V1 sin theta 1. Similarly for V2 cos theta 2 and vertical component is V2 sin theta 2. ठीक है so that means the force from this equation gives us the resultant force. Also write force along x direction and force along y direction. कैसे rho q V1 cos theta 1 minus V2 horizontal components and rho q V1 sin theta 1 minus V2 sin theta. So then you can find out the resultant force as horizontal के साथ एंगल जो है वो आ जाएगा आपके पास थीटा tan inverse Fy upon Fx. This is the angle of this resultant force with horizontal. So on the same lines, you can resolve P1 in the horizontal direction as well as in vertical direction. In horizontal direction, तो ये यहाँ पे होगा, and then in vertical direction. ठीक है? The angle is theta 1. This angle is theta 2. This horizontal component becomes P2 cos theta 2. और यहाँ पे जो vertical component है that becomes P2 sin theta 2. Here the horizontal component is this one P1 cos theta 1 and vertical component is P2 cos theta 1. Sorry P1. This is P1 cos theta 1. ठीक है? So on the same lines, the difference of pressure force along x and y direction you have to consider under force. So that means if I try to write Fx while considering the effect of pressure also, so the velocity momentum component is rho q V1 cos theta 1 minus V2 cos theta 2, then the component of pressure. So pressure along x direction 1 and 2, 1 minus 2. So 1 जो है that is this one in the same direction, x direction में है, positive x direction में है. So P1 intensity है P1 intensity है, this is आपके पास P1 cos theta 1. तो force आ जाएगी अगर आप इसको area से multiply करोगे. So that write as plus P1 A1 cos theta 1. Okay. Now you see on second section. So that second section you have P2 cos theta 2 x in the opposite direction. So this is the intensity multiplied by area give you the force. So that becomes minus P2 A2 cos theta 2. Similarly, you can write Fy rho Q V1 cos theta 1 minus V2 sorry sin theta के साथ आएगी ये टर्म V1 sin theta 1 minus V2 sin theta 2 plus P1 A1 sin theta 1. Now again you can see P2 A2 sin theta 2 acts in the downward direction. The component जो है वो downward direction में है. You can see in this diagram. So in that manner, you can calculate Fx, Fy, then the resultant force, and then the theta. Tan inverse Fy upon Fx. Okay. So in this manner, you can use impulse momentum relation or impulse momentum equation to determine the force exerted by fluid on the bend in the pipe. Okay. Now you can also see here rho Q. The term rho Q, we can also write it as WQ by G. लिख सकते हो W is rho G. Okay. So you can also write rho as W by G. So term rho Q, you can also replace by WQ by G. Okay. So this is all about your syllabus in first paragraph.